All right, well, good morning, everyone. Welcome to today's MIST seminar. And so today we've got Dan Whiter from the University of Southampton, and he's going to be telling us about neutral heating by the aurora. If you have any questions, you can drop them in the chat or you'll have the opportunity to ask them yourself at the end. Okay, over to you, Dan.
Yeah, thank you very much. And thank you to Miss Council for inviting me to give the seminar as well. As Matt said, I'm going to be talking about neutral heating by Auroral Electrodynamics and work which has been done in Southampton the past few years. So it's got my name there, but actually quite a lot of the work's been done by other people. So I'm going to include them as I get to their work. So just a quick overview of what I'm going to be talking about. I'll set out what the problem is we're trying to address and why we should quantify neutral heating. And then there's three different studies we've been doing using optical instruments. So firstly, measuring neutral temperature altitude profiles, and then imaging neutral temperature in aurora, and then measuring local electric fields around aurora. And then finally, I'll just give a very brief overview of our plans as the IceCat 3D radar comes online later this year or next year. Okay, so firstly, what is this neutral heating we care about? So ionosphere contains electric and magnetic fields, as I'm sure most of you know, and those electric and magnetic fields can drive ions in the ionosphere to have a different velocity to the neutrals, so to the neutral wind. And if you're driving the ions through the neutrals, that leads to collisions and frictional heating between the ions and the neutrals, so the neutrals can get a bit hotter. And this can actually be a lot of energy going into the upper atmosphere. So I took these numbers from this study, Knip et al. 22% of the total global upper atmospheric energy input is from this Joule heating, or from the heating caused by ion neutral friction. And it can be up to 70% in large storms. So this is a lot. If you think about comparing this to the energy input from just solar photons, UV photons, if 70% is coming from the ion neutral collisions, that means it's about at least twice as much as the UV photons. So it's a lot of energy input. And that needs to be included in atmospheric models used for things like climate predictions, and also looking at drag on spacecraft and space debris, because as the atmosphere heats, it expands upwards, and that increases the drag on these things in space, which we need to know about. So a lot of work has been done by a lot of people recently trying to quantify this Joule heating and incorporate it into these atmospheric models. Okay, so it's something we need to measure. The problem is that it's not that easy to measure. It's most often been done, I think, using superdarn, or at least by radar, by measuring electric fields, and then you can calculate a Joule heating rate from the electric field and from either measurements or models of neutral wind. These measurements would typically have a resolution of maybe 2 minutes and a spatial resolution of about 100 kilometers. And that can actually lead to an underestimate in the calculated Joule heating rate. And the reason for that is that the Joule heating is proportional to the square of the electric field. And I just made a quick cartoon here to show that the square of the electric field is not the same. Sorry, the mean of the square electric field is not the same as the square of the mean. Okay, so if you've got some averaging associated with a coarse temporal or spatial resolution, that's effectively like taking an average. And if you then square it, you don't get the same answer as if you take the mean of the square. So here I just created 100 random numbers, added on a couple of Gaussians, then squared them and calculated the mean, and I got 279, and calculated the mean and then squared that, and I got 140. So you see it's a factor of 2 difference. And in the context of electric fields in the ionosphere, you could have very strong electric fields adjacent to aurora, for example, and if you're measuring over 100 kilometers, that's all going to get averaged out, and it leads to an underestimate in the Joule heating rate. So Joule heating is difficult to quantify, especially where the electric field is highly variable or very strong. Superdarn is definitely important and is needed for the global scale, and a lot of good work's been done. But today I'm focusing on the smaller scales. So I'm just going to be looking at electric fields and heating adjacent to the aurora or within the aurora on much finer scales, so higher temporal resolution and spatial resolution. Okay, so the first part of the work which I'm going to be talking about is measuring neutral temperature altitude profiles. That's work which has been done using HITEYES, which is a spectrograph. High throughput imaging and shell spectrograph, excuse me, is located on Svalbard at the Shell Henriksen Observatory. This is the roof of the observatory, and I think that dome is the one that's got HITEYES in it. And this is work which was mainly done by David Price for his PhD. He's just finished. What is HITEYES? It's a graph. We actually use a mosaic filter on this instrument, and the reason we do that is in most spectrographs you need to have a trade-off between resolution and wavelength coverage. So if you have a broad wavelength coverage, you need a coarse resolution. You have to have a coarse resolution, whereas if you have a fine resolution, you don't get to see much of the wavelength range. Whereas with this mosaic filter, we can select multiple overlapping spectral orders, and we can get a high resolution, but look at different parts of the spectrum. So here we've got 3 panels in this mosaic, looking at these different wavelength regions. It's actually only this central one, which I'm going to be concentrating on today, which we call the O+ panel, although it also has N2 and OH in it. So we get a high spatial wavelength resolution for about 1 angstrom within this wavelength range. And the other advantage of using this mosaic filter and an imaging detector, so we image this with essentially a camera at the bottom of the spectrograph, is that we get wavelength information, but also spatial information. So wavelength ends up in the Y direction on this mosaic filter, and then the X direction is the position along the spectrograph slit, and that means we can get spectra at different positions in the sky along that slit, and you'll see why that's useful a bit later on. Because this is a kind of spectrum we measure from that central O+ panel. The grey crosses the data, so this is for one specific time, and this is the spectrum, and it's made up of multiple different components, and we have this fitting technique to separate those out. So the green peaks you see here, this is OH air glow emissions, so that's always there. It's not aurora, that's air glow. The orange is O+ emission, which is aurora from low energy electron precipitation, and the purple is N2 aurora, and that's the one I'm going to be focusing on now. And then there's a grey constant background, and the black line is the sum of those, and you see in this case it fits well. So we've separated out the OH, O+, and N2 components, as well as this constant background. Okay, so let's just have a look at that N2 spectrum in a bit more detail. We can model it, create synthetic spectra, and it depends on temperature. So the top panel here is a synthetic spectrum for a temperature of 200 Kelvin. So that's the N2 neutral temperature. It's actually a rotational temperature, but it should be the same as the neutral temperature in the E region. Okay, and there's many different spikes here, and these are all the emission lines associated with different rotational and vibrational energy levels within the N2 molecule. So if you have an atomic emission, you get 1 or 2 spikes associated with different transitions between energy levels. In molecular emissions, because there's so many different energy levels associated with those rotations and vibrations, you get many emission lines. And then I've convolved those with the instrument function for the spectrograph, and we get this black line. So that's the sort of thing we would observe. And then the bottom panel shows that for different temperatures. So stepping up from 200 Kelvin to 1000 Kelvin, and you see it's temperature dependent. So from the observations and by fitting different temperature synthetic spectra to the observations, we can work out the temperature of the N2, which was emitting around 120 kilometers, say. However, it's not actually that simple, because the N2 emission comes from a range of altitudes. So this is just an example N2 volume emission rate profile in a dashed line here. So this is like the brightness of the aurora as a function of altitude, which is on the y-axis. And you see it's distributed over quite a wide range of altitudes, and it's in a region where the neutral temperature varies a lot. So the solid line is the neutral temperature profile just taken from MSIS for some particular day and conditions. So this is an example temperature profile, And over this region where the N2 is being emitted, the temperature is varying from, say, 200 Kelvin up to 800 or 1000 Kelvin. So the spectrum is not well fitted by a single temperature. It's this whole temperature profile. So that's a problem, but it's also an advantage because it means that that spectrum contains information on this altitude profile, and that's what we are trying to retrieve. Incidentally, the OH volume emission rate profile is much narrower. So other work has looked at the OH neutral temperature, and that's well fitted by a single temperature because it's a thin layer. The N2, which is higher up in the E region, it's not a single temperature, it's this profile. Okay, so then how do we retrieve that profile? I'm just going to take you through the steps in the inversion process we use to go from the observed spectrum to the neutral temperature profile. So firstly, we need to get the energy influx of the electron precipitation. I'm not going to go into a lot of detail about that now, but I'll come back to it again a bit later. For now, just know that we use a different instrument called ASK, which is an imager, and it looks at two different emissions simultaneously, and those emissions are sensitive to different electron precipitation energies. And so by looking at those simultaneously, we can work out what the energy influx of the precipitation is. Once we've got that energy influx of precipitation, we can put it into our ionospheric model, and that models production rates of various ions and neutral species as well, and also emission brightnesses. And the thing we want from it for this work is the N2 volume emission rate profile. So the brightness of the N2 aurora as a function of altitude throughout some auroral event. So we get that from the model. We also get electron densities, which we can verify, or we can use to verify the model with ice cap measurements. So the ice cap radar measures electron density profiles. This is one particular event which we modeled, and this is the ice cap data of electron density. And this is the electron density we get from the model. And you see it matches very nicely. Something went wrong with the ice cap fitting here, so don't worry about that part. But the other parts all match nicely, which means we have some trust in the model. So we can trust that we've got decent estimates of the N2 volume emission rate profiles. Once we've got those N2 volume emission rate profiles, we combine those with trial neutral temperature profiles and make a synthetic spectrum which corresponds to that temperature profile instead of a single temperature. So here's a volume emission rate profile we got from the model, and here's just a test temperature profile. And what you just saw was it being integrated up in altitude. So we take temperature at each altitude step, calculate the spectrum for that temperature, and then weight it according to the volume emission rate at that altitude or the brightness at that altitude. Add them all together or integrate up, and we get the spectrum, which is now for this temperature profile instead of just a single temperature. And we can do that for many different trial temperature profiles, fit those to the height-ized measured spectrum, and essentially choose the best one. And that tells us what the temperature profile was instead of a single temperature. Okay, and we quantify the best one using the residuals between the synthetic spectrum and the observed data, and we use the root mean square of the residuals to quantify that, how good the fit is. Okay, so that's an overview of the process. It's still challenging, and that's because of this thing we call degeneracy, where you could have very different temperature profiles which end up producing very similar spectra. So here I've got a neutral temperature profile from MSIS in black, and then it's just been flipped in red, which is completely unrealistic, of course, but it ends up giving a very similar synthetic spectrum. And the reason is we don't really know which altitude different parts of the emission came from. So in this case, these two different profiles give similar spectra. So another way of looking at that is to think of the parameter space, which is defined by the temperature profiles, as many local minima, i.e. many different temperature profiles will fit the data. We want to find the true profile and the best fitting profile, which is the global minimum. So we don't want one of these local minima, we want the global minimum. And to do that, we use a technique called simulated annealing. Annealing is where you cool some metal slowly and you hammer it and you push it into a low energy state where it's strong by cooling it slowly and repeatedly hammering it. This is a a simulated version of that where we're hammering these temperature profiles instead. So we take some trial temperature profile, fit it to the high TICE data, see how well it fits. Then we iterate through, and at each iteration we take a neighboring temperature profile, so a similar profile to the previous one, and then we then fit that to the high TICE observations instead. If it's better, so if it gives a better fit, we accept that new profile as the new state of the system. If it's worse, we might still accept it according to some probability, which is this exponential function. So we take the difference in the how well it fits, so the root mean squares of the residuals, divide it by this T, which is some parameter of this simulated annealing, called the system temperature or annealing temperature, and that's analogous to the temperature of your metal which you're cooling. And then it's a negative exponential. So as this temperature cools, we're more and more likely to accept, we're less and less likely to accept worse profiles. So if it's a worse profile, if this temperature is high, we're highly likely to accept it, even though it's worse. As we iterate through, we reduce the temperature, we become less and less likely to accept worse profiles. And by doing this, it means we can escape those local minima, because we can climb a hill out of those local minima by accepting worse profiles, and the system ends up cooling into the true global minimum. I'm just going to show a video to show how this works in practice. So here, we wanted to verify how well this works. We took an MSIS neutral temperature profile. We created a simulated data from that, added some noise, and then put it through our inversion process to try to retrieve the profile which we knew we should get. The dashed line here is the volume emission rate profile of the N2. What you're going to see here is lots of different temperature profiles appear on top, which are the trial temperature profiles we're fitting to the data. And then in this panel, you'll see how well they're fitting, which is this RMS of the residuals. So lower values mean they're fitting well and they're color coded. So the red ones here are better. And then this is going to build up as we run through the iterations in this simulated annealing process. In blue will be the annealing temperature, which controls how likely we are to accept worse profiles, and that acceptance probability is up here. So if I run that through. Okay, so the color profiles are the different trial temperature profiles, and then this is the fit statistic, so how well it's fitting to the data. And the yellow ones we've accepted, and up here is the acceptance probability. So sometimes they're worse profiles, we still accept them. The grey profile is the current state of the system, which is like our current best profile. We run this through 3 times and average the results to make sure we find a good outcome. And as you see, when we get near to the end of one of these runs, this grey profile starts following the true profile pretty well. That one was especially good. So as this system, the annealing system cools, this profile gets nudged towards the profile we want to achieve. Okay, and once we've run it 3 times, we've got about 9,000 different trial temperature profiles and a measure of how well they fit the data. Then we take actually all of those profiles and calculated a weighted average, which is shown in red here. That's the weighted mean of all the trial temperature profiles, and then a weighted standard deviation as an estimate of the uncertainty. And we were really happy with this because you see it fits the profile we wanted to retrieve pretty well. So we were confident that we could retrieve profiles in Aurora. We tried it with other trial profiles as well, of course. So this one is a much cooler profile, and again it retrieved that one well. These dashed or dotted lines are where the volume emission rate has reduced to 5% of the peak. So outside that region, there's not much emission there, so it doesn't constrain the fit very much, and so we start to get less well-fitting results at the altitudes above and below those regions. So we ignore those regions and we just take the portion where the volume emission rate is at least 5% of the peak. This one was a hotter one, and again you see it retrieve the profile which we wanted well. Another thing to notice here is that the uncertainty goes down where the volume emission rate is higher, because that region is contributing more to the measured spectrum. So it makes sense that we'll be able to constrain the profiles higher in those regions, or better in those regions. We also tried this with some bumps in the profile, temperature profile, because we thought if there's heating, maybe it's not going to be a nice smooth profile, we might get some bumps. And it still does a pretty good job of retrieving those. It does smooth out the bumps, but we were happy that this generally follows the shape of the profile. And this one ended up with a very steep temperature gradient around 120 kilometers there, and then it flattens a lot. So this bump also got smoothed out, but we're still pleased that it does a pretty good job of retrieving those temperature profiles. Okay, so once we were happy with the technique, we applied it to some data. This is a video from the ASK camera of the N2 aurora, and this is just a small region of the sky, and this is running at real time, so I'm hoping it's playing okay over Zoom. But this shows what was going on in the aurora in this 10 kilometer by 10 kilometer region. And in red, white, and blue here, this is the spectrograph slit. So that's where we can retrieve the neutral temperature profiles. And because we have that mosaic filter and an imaging detector on the spectrograph, we can divide the spectrograph slit into different parts. And we've divided it into 3 parts here, which is the red, white, and the blue parts. And on the right here, you see the neutral temperature we retrieve from those different parts of the spectrograph slit. I'm going to pause it at some points in a moment just to show you what we saw. But you see that this is a time resolution of a few seconds. I think we went down to 1 second. We did vary the integration time depending on how bright the aurora was to make sure we got a decent signal to noise ratio, and we were happy with the fits. But I think that's 3 or so seconds at this time. So we've got this arc approaches the slit and then moves in. So let's see what we saw in the temperature profiles. So at this time, the red part of the slit was within the aurora, the white and the blue were adjacent to the aurora. And if we look at the temperature profiles we get at that time, the white and the blue are much hotter than the red. So these parts are adjacent to the bright aurora, and that's where there should be a strong electric field. So in an auroral arc, you get an electric field on either side of the arc, which points towards it. So we think there's a stronger electric field here adjacent to the bright aurora, and that's driving those ions in a different direction to the neutrals, and that's what's producing frictional heating and Joule heating and increasing the neutral temperature profile in those regions. It's actually very significant, or it's very strong, I should say. A few hundred Kelvin maybe difference, and also the temperature profiles change very rapidly. So I think in the dynamic aurora, the temperature really does change a lot with the variation in strong electric fields. We studied a different event first as well, actually, and that's been published in this paper, so you can go and have a look there. Measurements of the Joule heating adjacent to a bright arc. Okay, a bit later on, the arcs moved into the white part of the slit as well, and now the white part is cooler, and the blue part adjacent to the arc is hotter. So again, that's where the electric field is strong adjacent to the arc. If I move slightly further in the same event, here the aurora is actually brighter, but we scaled it down so you can see it clearly. And we had this curl system which moves through the spectrograph slit. So there's some curls going on the aurora there, and there's this bright curl which goes through. Because it was brighter, we could reduce the integration time, and we get temperature profiles at higher temporal resolution. Okay, and what did we see there? So before the curl went through, we got these temperature profiles, and then as the curl moved through, I've reproduced these temperature profiles in dots on this plot just to show the differences, and then the solid profiles here are from when that curl is in the slit. So you can see when the curl is in the slit, the temperature is much hotter than before it entered. So this is different to Joule heating adjacent to the arc, because the Joule heating adjacent to the arc is where there's strong electric fields which drive that ion neutral frictional heating. Instead, in this case, we think it's strong field line currents embedded within the curl. So the idea is these curl systems are on some current sheet which has got Kelvin-Helmholtz instability causing the curl on the current sheet. So if we've got this strong field line current there, we get what we've termed ohmic heating following the terminology from this Manchester paper. So that's electron precipitation, currents carried by electrons passing through the neutrals, colliding with the neutrals and heating them. So we think this is different to the Joule heating. And it's observationally, it's different because in the bright aurora it's hotter, whereas in the Joule heating, in the bright aurora it's cooler. So here we're getting this strong heating from this field line current. A bit later on, the curl was still in just part of the slit, and the blue one has started to cool. And then after the curls passed out of the spectrograph slit, again it's cooled further. So within the curl we had these hot profiles, and then we're not out of the aurora yet, so I don't think we're in the region where there's strong Joule heating and strong electric fields, but we're out of the region of intense field line currents. So the temperature's cooled. Okay, so there's two different types of heating we could see in the fine scale aurora: the Joule heating adjacent to the arc, and then ohmic heating from field line currents within the arc. And I just took the temperature at 130 kilometers throughout that whole event. So the first part of the event I showed was where we saw the Joule heating, and that's here where we've got these elevated temperatures at 130 kilometers. And then as the bright aurora moves in, temperature decreases, and then this bump is where that bright curl went through. So that's what we think is this field line current embedded within the curl, causing the heating there. And then on the tail end of the arc, I haven't shown in this case, I'll show it somewhere else in a moment. We also got heating, but it's less intense than on the leading edge of the arc. So that's the two different types of heating going on there. Okay, the next section of the talk, I'm going to be talking about imaging neutral temperature. So I'm done with the profiles for the moment. And this work is using another instrument we have on Svalbard called ASK, which stands for Auroral Structure and Kinetics. And this is an imager which observes with three highly sensitive electron multiplying CCD cameras simultaneously. And the reason we have three of them is to look at three different specific emissions. So they each have a different narrow passband filter to select specific auroral emissions. And they have optics on top to produce a 3-degree or 6-degree field of view. So there's some telescopes which we can take on or off the instrument to reduce the field of view down to 3 degrees. In the E region, that corresponds to about 5 kilometers or 10 kilometers. And all three cameras are looking at the same part of the sky, centered on magnetic zenith, and we can run at either 20 or 32 frames per second, depending on how likely we think something interesting is going to happen. Just to put that field of view in context, this is an all-sky camera image, so that's a 180-degree field of view, and this is the size of the 3-degree field of view. So we're really looking at the fine scale stuff within the aurora, just in that narrow region. The images I just showed you, the event I just showed you, that was a 6-degree field of view, so it was double this size, but it's still small compared to the whole sky. Okay, so these are the wavelengths we look at. The videos you saw so far were from this N2 emission. The other two cameras, the third one has always had this atomic oxygen emission, and then the second one, we used to have this O+ filter, and I've recently changed that. I'm going to explain why. What can we do with those? So the ASK1 camera with this N2 filter observes this emission at 673 nanometers. And here I plotted the emission brightness as a function of electron precipitation energy from our model. And then the orange line is for this other emission observed by the third camera. This 7774 nanometer emission is a result of two different processes. One is electrons impacting on atomic oxygen directly and exciting them. And the other is electrons impacting on molecular oxygen, which then dissociates into atomic oxygen. And you can get the emission that way as well. So there's two different contributions to this emission, which are sensitive to different energies. But if you add them up, you get this orange line showing emission brightness as a function of energy. You see these two emissions are sensitive to energies in different ways. And if we take the ratio, this black line is the ratio of the orange over the blue. So the oxygen emission over the nitrogen emission. And we can observe those two emission brightnesses, calculate this ratio. And when we've got that ratio, that tells us what the energy of the precipitation is. So earlier on, when I first started talking about the temperature profile inversion, and I said we needed the energy and flux of precipitation, this is how we do it. So we observe those two emissions, take the ratio, and that tells us what the energy is. This other N2 filter, I installed that in January 2020, and that filter is designed to be able to image the neutral temperature. I'll show you how that works. This is the original filter we've had on ASK1, which we use to retrieve the energies, and the black dashed line is the filter transmission curve. So it's how much light gets through the filter as a function of wavelength. And then underneath is the, in color, is the N2 spectrum for different neutral temperatures. And you see it varies, but actually through this filter, the intensity, the total intensity doesn't depend on temperature very much. This new filter, which we installed, is looking at a part of the spectrum where the intensity does depend strongly on temperature. Okay, so it's narrower and it's looking at slightly redder wavelengths, but it's on this part of a band system, which is the higher energy transitions associated with the higher temperatures. Okay, so because this one is strongly dependent on temperature, we can do a similar thing to to get the energy and flux, and we take a ratio. So here, instead of energy, I've got the neutral temperature and those two emission brightnesses. This 673 nanometer one is approximately constant with temperature, but the other one is not. And so by taking a ratio and observing that ratio, we can work out what the temperature of the emitting N2 is. Okay, so this is some preliminary observations. So I installed that filter January 2020, and then quite a few things broke, unfortunately, and the pandemic came along, which meant I couldn't go and fix them. We did go up in December, just gone, and managed to fix a lot of things. But these are observations I got just before some things broke, so February 2020. This is the aurora through the ASK1 filter. So that's just showing you the structure of what's going on in the aurora. And then this is the neutral temperature determined from the two end. And this is the electron precipitation energy from the oxygen and first N2 filter. And these have been binned to increase the signal to noise ratio. Unfortunately, I think there's some calibration issue with the first filter. I think the filter transmission curve has possibly aged. I was hoping to fix that when we went up to Svalbard in December a few weeks ago, but I couldn't, so I need to bring the filter back to Southampton to recalibrate it, which I'm hoping to do this summer. So these scales I don't trust completely. This I think is much colder than it should be, but qualitatively I do trust the results. It's just I think this should be probably multiplied by a factor of 2 or something. And similarly, these energies have come out way too high, I think. And I think it's this calibration issue which we fix later. But I can still show you what kind of things we see. So firstly, this is running at I think 32 frames per second. It might be 20 frames per second. So we're getting these neutral temperature maps at 20 frames per second. So that's much faster than anything that's been done before, I think. And also the spatial scale is tens of meters. So looking at the heating where the electric fields are really locally very strong. So I'll just pause that at some points. So here, as the arc moved into the field of view, we saw temperatures got very hot in this region just adjacent to the arc. There's still enough aurora there, still enough light there to determine these temperatures, but it's adjacent to the brightest part of the aurora. With these temperature images, we do need to be careful to think about where the emission is coming from, because the height of the emission depends on the electron precipitation energy, so it does come from different heights, but we're not getting profiles in this case. We're just getting some kind of average temperature. So if the energy goes up, then the emission comes from a lower altitude, and we might expect the temperature to be cooler there, or to be at least different. In this case, if we look at the energy image, these two regions have very similar electron precipitation energies. So the emissions should be coming from very similar heights. But if we look at the temperatures are very different in those regions. So I think this is actually Joule heating adjacent to the arc. Temperature's gone up a lot, and it makes sense. This is where there's going to be very intense localized electric fields adjacent to the arc, causing this massive increase in the temperature there. Another thing, so there's also hotter temperatures on the trailing edge of the arc as well, but not quite as hot. And it's actually not surprising that the temperature is asymmetric on either side of the arc. This is just a little cartoon to show you how the electric fields should be, or we think they are, around an arc. So here's an auroral arc. The electric field associated with it is intense and pointing towards the arc on either side, but that's superimposed on top of some background electric field associated with global convection. And on one side of the arc, those convection electric field and arc associated electric field will add up and produce a stronger total electric field. And on the other side of the arc, they don't cancel completely, but they will slightly cancel, which means you get a reduced electric field. It's still intense, but not as strong as on the other side. So here, where the temperatures are not as hot, that's probably on the side of the arc where the convection electric field and the arc associated electric field are opposing each other. Whereas the leading edge of the arc, we probably had a much stronger total electric field. Something else I picked up in those observations are these narrow regions where the temperature is increased. It's not as much as in the Joule heating, but it is increased there. And if we look at the energy, there's not much structure in the energy. So this whole region is probably coming from the same altitude, and this is probably actually hotter temperatures in some narrow filaments. That might be intense field line currents in these filaments, but this is just preliminary observations, and I need to look at this in more detail before I fully understand what's going on in there. But that could be intense heating associated with field line currents. Okay, so now moving on to something a bit different. The other ASK filter, which I haven't discussed yet, is this O+ filter looking at a long-lived emission. This filter has been on the ASK2 camera for most of the instrument's life before I replaced it with the other filter for making the temperature maps. And the reason we want to look at this emission is because it's long-lived. It has a lifetime of about 5 seconds. It means that once the ions are produced, then the ions will drift from that production site before they actually produce the emission. So we see the emission after they've been produced, or some of them will emit straight away. It's a statistical process, but on average they will drift. So if I show this cartoon of what we might expect to see in a prompt emission, like the N2 emission, so we've got some production going on here, some precipitation which is producing that emission, and it's producing emission in both filters. Sometime later, the production has stopped, so this prompt emission is turned off, but we see this long-lived emission drift from that production site. And we look at where the emission has ended up, and we could track that drift, and then work out the velocity of those O+ ions. Or we might see that the production continues and you get some kind of plume form where the ions are drifting away from this production site before emitting. In reality, it's probably is a combination of these things. So you get drifting production, which turns off, and then the long-lived emission stays around for a few seconds and drifts as it stays around. But there's also plumes going on when the production is actually happening. So by measuring these O+ drifts, then we can measure the electric field. And this comes from around 250 kilometers altitude. So it's where the drift should be able to give us the electric field without having to worry about the neutral motion too much. And in this section, this work has mainly been done by Sam Tuttle, who's a former PhD student, and Patrick Kuchelik, who's a current PhD student who's taken on this work and extending it. Okay, so how do we get those ion velocities? So firstly, the O+ emission brightness, which we observe with ASK, we can calculate that if we know the O+ density. You just multiply it by an Einstein coefficient, which is like a transition probability, and that gives us an emission brightness. And that Einstein coefficient is reasonably well known. Of course, we'd always like more accurate coefficients, but it's reasonably well known. So we know that one. Then we want to model this O plus density. Because this is long-lived, we need a continuity equation for the O plus density, which is a differential equation giving us the change in O plus density as the sum of production terms minus loss terms minus transport. Okay, so we solve this equation to work out what emission brightness we should get. So the production terms, we get those from the energy influx of precipitation from the other two ARS cameras. We put that into the ionospheric model, and that gives us the production rates of O plus. So we can get the production. The losses are, there's two different types of losses. There's quenching, which means collisional, well, the O plus collides with something and it either de-excites or it stops being O plus, it becomes atomic oxygen, for example. Quenching is by atomic oxygen, N2 or electrons, and we can get the densities of those from our model or from MSIS, and we know the quenching rates, so we can calculate those losses. And then there's also losses by emission, not just this one we observe, but also other emissions at different wavelengths. And for those, again, we know the Einstein coefficients, so we can calculate those loss rates. So then the only thing we don't know is the transport. So that's the movement of the ions and the ion velocity, which is what we want to know. So we do that by trial and error. We try different transport, calculate images which, or modeled images which we'd expect for a given transport, compare those to the observed images from ARS2, and then whichever transport gives us the best match between the modeled and observed images, we take that as the ion velocities. So originally we just had a constant ion velocity over the image, but Patrick is now extending that into what we call the double flow model, where this transport part has 5 free parameters and we have different velocities on either side of an arc, for example, because we know the electric field should be different on either side of an arc, so ion velocity should be different as well. So the 5 free parameters of the transport are position and angle of this separatrix, which separates 2 regions of different velocity vectors. So that would lie along an arc, for example. And then we have velocity parallel, or components of velocity parallel to the separatrix on either side, and then a velocity component across the separatrix, which is the same across the whole image. So those 5 free parameters, we try different versions of those and until we get images which match the observed images, and we then know what these ion velocity vectors are. So this is results from Patrick for an event he's been working on. So this is the observed O plus emission from ARS2, and then this is the results of the model for a certain set of ion velocity vectors. And the black lines are showing the contours from this modeled images. So it's just to show that it matches nicely. So we think we now know what the transport term is in the continuity equation, so we know what the ion velocities are, and from that we can get the electric fields. Okay, so these are the results of the ion velocity in the northern part, so above the separatrix, and the southern part below the separatrix. And because we solved this at the resolution of the ARSC observations, we can get the ion velocity vector at a 0.1 second cadence with that overall feature. So the blue lines are the O plus ion velocity at different times over that, I think it was 4-second period. And the red is the velocity which we retrieve from superdarn over ARSC at the same time. That's averaged over a much longer time scale, but within that superdarn time interval, those are some of the velocity vectors we get. And then also Anna from UCL gave us the neutral wind measurement from the Scandi instrument. So from the neutral wind and the ion velocity vectors, well, from the ion velocity vectors we can get electric field vectors, and with the neutral wind vector we can calculate Joule heating rates. So Patrick's done that as well. And this is the Joule heating rate over those 4 seconds for the northern region and the southern region of the image. So we got the 2 different electric fields on either side. And then the black is the Joule heating, which will be calculated from superdarn and we see what we expected, I guess, that the electric field around the aurora is more intense than the average from superdarn, but it's very spiky as well. So it has intense periods for a very short time. So say this spike lasts for about half a second, and at that time the Joule heating rate was about 10 times higher than the Joule heating rate which will be obtained from superdarn. So we're trying to look at the to quantify how much the averaging matters when you have a core spatial resolution, and try to look at what heating rates we actually get close to aurora where the electric fields are very strong, locally very strong. Okay, so this is Joule heating derived around that arc. And then the next step, which Patrick started working on, is to use the neutral temperature profiles we get from high tides to calculate Joule heating profiles as well, not just an integrated Joule heating rate. Okay, so that's most of what I wanted to show you. Just finally, I'm going to talk about plans for next year. So many of you will know that IceCat 3D is coming along. This is a new incoherent scatter radar system currently being built in Norway, Sweden, and Finland. All the observations I showed you today are from Svalbard, so in the Arctic up here, but we successfully got money for a new 4-camera ASK system, which we're going to be installing at Skibotn next to the IceCat 3D transmitter site. And this will be a joint instrument between Southampton and Northumbria University. So when we're running that together with IceCat 3D, we should be able to do a lot more than we've been able to do so far. And also it's going to be 4 cameras instead of 3 cameras, so we can get the electric fields and the neutral temperature images at the same time. At the moment, we can only get one or the other, not both together. So what does IceCat 3D give us? IceCat 3D is going to give volumetric measurements of ion velocities. So the existing IceCat radar, you used to be able to determine ion velocity vectors in a single beam. With IceCat 3D, we can put multiple radar beams on the sky. So this is just an example of what we might want to do. Here's an example image. And then we could put these radar beams on here, and we get ion velocities at each of these beams as an altitude profile. The radar time resolution actually still won't be good as the optics, but by using those radar measurements of ion velocities, we'll be able to constrain the modeling that we're doing using the optics and get a much better fit and much better estimates of the ion velocities and so electric fields over this image, and hopefully be able to parameterize it into more than just 2 regions, but many regions within the image. So we can look at variation in electric field with distance from the arc, for example. The radar will also give us electron and ion temperatures, and also electron densities, volumetric measurements within this region of space. And using those together with the neutral temperature measurements from the ASK camera, we'll be able to get conductivity maps. So we can make maps of the conductivity at high resolution around fine scale of all features. So start looking at where the current is flowing and what's going on with the auroral electrodynamics at this very high resolution. And part of that work is to work towards estimating how much Joule heating is being missed by the averaging from the larger scale measurements, and look at how much Joule heating there is around these fine scale auroral dynamics. And that's everything. Thank you very much.
Thanks a lot, Dan. Really interesting stuff. I think we can give Dan some virtual applause with the reaction thing, or maybe we can't. Maybe can we raise hands down there? But yeah, thanks very much. Really appreciate it. Mike Lockwood had a question in the chat. Mike, do you want to unmute, or would you like me to read that out?
I can unmute. Dan, I was wondering, because we'd really quite like to know the exospheric temperature and your nitrogen emission profile when you're doing the profile stuff. That's never going to give you enough emission high enough to be reliable up there, is it? So I wondered if there's another line you could use in the same sort of way.
Yeah, the other issue with the N2 at very high altitudes is I don't fully trust that there's the rotational temperature is the same as the kinetic neutral temperature. Right. So at very high altitudes, yeah, I wouldn't trust the nitrogen measurements. If I can skip back a long way. There is a line which might be able to give us temperature, and that's from the O+ emissions. Sorry, it's early on in the talk. Okay, yeah, these the lines in orange here, these come from O+.
Yeah.
This is actually two different doublets, and I think this ratio should give us the neutral temperature at 250 kilometers. I did a study of this ratio, a statistical study, and published that a few years ago, but we haven't been able to verify that it's actually giving temperature yet. But actually I have a PhD project advertised, and I'm hoping for a PhD student to start looking at that again in October. And if we find that this ratio does give us the neutral temperature, that will be around 250 kilometers altitude, and it's quite interesting. I think the O+, the production of the O+, there's two different states in the upper. The upper states is actually two different total angular momentum quantum numbers, and I think there's some kind of conservation of angular momentum, so that when it gets ionized, the distribution of those states follows the distribution of atomic oxygen states, which is thermalized. So maybe we'll be able to get exospheric temperature using those.
And would you be able to do that with the same instrumentation you've got now, or would you need another instrument alongside to do the nitrogen?
No,
and
yeah,
the oxygen?
we can do that with high ties. Once we've fitted this, we get that ratio, so we can do that with high ties. High ties is on Svalbard at the moment, but I may move it to the mainland when IceCat 3D comes online. Haven't fully decided yet, or maybe we can get some other instrument to look at it. But yeah, we can get that ratio.
Yeah, good.
Other questions for Dan? If not, I had one about the previous slide to this one, actually, your event study where you modeled it. Oh no, it wasn't. Maybe one more. There was you had the observations of electron density.
Oh, right.
The model results on the bottom. It's fairly early on in the talk.
This one.
One previous. There we go. That one there. I mean. Oh,
I think you've got a lag from me. Sorry.
Oh, there you go. Yeah, that's the one. I mean, the agreement's really impressive. The only discrepancy that jumps out at me is that it looks like the electron density drops more rapidly after the storm than the model predicts. Yeah. Is there a reason for that?
Yeah, it's transport out of the beam. So the IceCat is measuring electron density profiles in about 1 degree beam. In the model, it's a one-dimensional model, so it's one field line.
Right.
And we get production of ions and ionization and electron densities on that field line. Gotcha. And at the moment in the model, we don't have, the only way of destroying the electrons is by recombination, really. So they don't get transported horizontally out of the beam.
Right.
I'm hoping to expand the model to 3 dimensions at some point, but that's...
Yeah, but I mean, it's already a really nice example about how modeling can give you more information about the observations. Really nice. Sorry, I see Anasuya's got a hand up. Do you want to unmute and ask your question?
Yep. Can you hear me? Yeah.
Yep.
Great. That was a fabulous talk, Dan. That's really, really exciting what you've managed to achieve. And I was really interested that you're seeing hundreds of Kelvin difference in temperatures over minutes, so huge variations. And when the thermosphere is a very sort of slowly responding behavior. So you're going to get a lot of changes in local chemistry as well. And with that heating, you're going to get upwelling. And so how do you think this will affect the processing of, say, the IceCat data, which tends to use MSIS as a model for the background neutral temperature?
Good question. Yeah, I hadn't thought about the processing of ice scatter data. I think this is all, it's very localized. So far from the aurora, I don't think that the temperature is going to be raised as much, of course. But yeah, within a small region adjacent to the aurora, you're right, I think the chemistry is going to change a lot. I need to think more about, because I'm looking at temperature rather than heating. So I need to think more about going from the temperature to the heating and also working out how the cooling happens, because there's going to be expansion, which will cause cooling, and also then just maybe that region of neutral atmosphere just drifts away but stays a bit hotter. And then also thermal convection.
Yeah.
Sorry? Yeah.
Yes, so a complex feedback system.
Yeah, exactly. I was surprised when I saw the observations how quickly the temperature changed. I was expecting to see some kind of plume or something like that on the temperature, but that's not what's there. So the cooling seems to be happening quickly as well.
So where are you going to put these 4 new asks?
It's at the Sheboygan Optical Observatory. It's pretty close to IceCat 3D transmitter site.
But will they be so they're not 4 separate instruments separated?
No, yeah, it's four cameras underneath one dome, looking at the 4 different emission lines. We want to look at the same point, because otherwise we can't take the ratios and we can't do this stuff.
Okay, and so if height is really important because of the temperature profiles, the height profiles, how are you going to be able to confidently distinguish between changes in the emission height and actual changes in temperature?
So we get the electron precipitation energy from 2 of the cameras and from the radar electron density profiles, and once we've got that, then it's this process. Not that one. We get the N2 volume emission rate profile from the model if we know the electron precipitation energies. So once we've got the N2 volume emission rate profile, then we know we're imaging some kind of temperature, which is an average over that region. It still has the problem that the temperature is going to be variable over that altitude range. Which is why it would be nice to move the spectrograph there as well, because then we can get the temperature profile.
But there'll be sort of implicit assumptions about sort of the inertia of the system in your model. So will your model respond rapidly enough so you can be confident that your height is correct?
So the model, yeah, it does use the N2, O2, and O profiles from MSIS at the moment, and if those are changing rapidly, then yeah, you're right. Maybe we need to correct that in some way, because the N2 emission is prompt and it's relatively simple. You just need the neutral density profile to get the volume emission rate profiles. But yeah, you're right. If the neutral density profile changes quickly, then it needs correcting.
Yeah, but congratulations. Yeah. That is a fabulous piece of work doing.
Thanks.
Great. Okay. Well, thanks everyone. Thanks for the questions as well. See you all on March 1st for the next MSIS seminar. The speaker's not quite been confirmed yet, but we'll announce it via email shortly. Okay. Goodbye.